time, we talked about the central limit theorem. Does that ring a bell to either of those of you who weren't here? The central limit theorem? That's right. We'll talk about what we'll make those things available to you. But I think we can go on. Some of the general principles will be revisited early here. Okay, so today we're going to talk about, hi Billy. It doesn't actually look like it's recording to me, even though we did it. Thank you, Billy. Sorry, I should have checked that. Next time I'll do it. Okay. So today we're going to talk about sample size estimation, which is, it's a thought experiment, right? In the sense that before you do your study, when you're in the planning phases of your study and you're thinking things through, you're going to ask yourself, how many patients do I need to be able to detect the difference, the statistical differences that I'm interested in. Now, when I was learning about sample size analysis, the assumption is there's a lot of data floating around that you can base your sample size estimation on. The truth is sometimes there's not, because you're doing a study because there isn't a lot of information on the research question you're looking at. There sometimes isn't a lot of work in that area, and without work in that area, for you to get a sense of what is the mean of interest, how different the means in two different groups would be, what's the spread of this measure in both your groups, those kinds of things is sometimes not available, frankly. So then, that's why it's a thought experiment, in the sense that you need to find some data somewhere, and oftentimes you'll have, if it's not a completely new measure you're interested in, and for example, it's not some new biomarker that you've just developed in your lab, which I don't expect you guys to be working with necessarily, there will be information on that measure in a different disease, in a different population, in something. And by using that, you'll have some base, i.e. you'll have a sense of what its mean tends to be and what its standard deviation tends to be. If you have that, then you say, well, okay, here's that. In the groups that I'm interested in, what's the difference in the means, the minimum difference that I'm interested in looking at? And then you'll go through a few steps, and which I'll talk to you about. And then you'll say, what if that difference in the mean is, well, you say you did it first time, you think, oh, that's too large of a sample. All right, let's flick it. If I can only recruit X patients here and X patients here, what's the minimum difference that I can detect? Does that make sense? And then I can say, what if the standard deviation is actually larger than this? What happens if I can only recruit these many patients? What will happen? Will it negate my ability to separate them and tell there's a difference? Okay? So first thing I'd say is a thought experiment. It really pays off to go look for information. If it's not there, you make it up and you go with it. And part of what you're doing is in the great arc of research in this topic, you're going to do some work that'll help the next person, possibly yourself, down the line.
So is this like a power calculation?
It is. The other way to look at this is a power calculation. So sample size is when you have a sense of the means, all of that, and then you're asking, and you say you want 80%, we'll talk about that, 80% power. Oh, how many people do I need? Power is, I can only recruit X. I know these things. How much power do I have to detect a difference? Two sides of a coin, right? And then we'll talk about a few of these things. I'll assume a little bit of knowledge. If you guys have trouble with things, just stop and that's what this is, a very small, informal group. So I've got 3 questions for you, and I just want you to give your gut impression. I'm going to give you these questions at the end. So this is about your own intuition on this. Okay? So question 1, what sample size, large or small, would be needed if there were a very large variance? Large. You don't have to answer me. Just check. But it's great. What sample size, large or small, would be needed if the investigator wanted the answer to have a smaller proportion of false positives? That is a small alpha, low p-value. Good.
Yeah.
Fair enough. So this is great. I don't want you to lose your intuition here. What sample size, large or small, would be needed if the difference that the investigator wanted to be able to detect was extremely small versus large. Small. Small difference. Bingo. So you notice that the answer is all large. And so, I always joke that don't ever ask a statistician what sample size you need because we'll always say large. That is quite true. Now, we talked about this last time, and for those of you, and in fact, I think the only person who was here last time, were you here, Fran?
No, I was away.
Oh, okay. Was you? You're carrying the flag, Hilton. And actually, I think, Wilma, were you here last time?
Partly.
Partly. So we'll spend a little time on this. So a lot of what we're doing, by the way, your intuitions were fantastic. Don't lose those. My goal here is not to make them go away by giving you some mathematical mumbo jumbo that will make you just scared and run for the hills. And so I've been very careful when I use a formula or anything, that it actually is needed and will help you. So a lot of the sample size estimation is based on the standard error definition. So remember, standard error is essentially, it's a statistical property. It's not necessarily measurable. It's based on something you potentially can calculate or measure, which is your standard deviation, calculate. So standard error is your sample's standard deviation divided by the square root of your sample size. And the standard error, what Hilton was probably trying to say, is the standard error, in some ways, is the standard deviation of your sampling distribution. And in the sense that it's in the population. And sampling distribution means that if you took a population and you took this sample and you took your standard deviation, you took this sample, took it, standard deviation, standard deviation, standard deviation, that kind of thing. The larger the samples you picked up, the tighter that sampling distribution would be of all those samples. So this one, so basically, as your standard deviation increases, as your variance increases, the standard error increases, and inherently your noise increases, and therefore you need more sample to potentially detect differences, which we'll come to in a moment. I'm trying to put these in new words, so hopefully I don't stumble too much. I try to. As your standard deviation decreases, standard error decreases. That is a direct relationship as opposed to inverse, right? Whereas as your sample size increases, the standard error decreases, your noise decreases in terms of looking at sampling distributions and all that. And sample size decreases, it goes up. Fair enough? So again, that's another. Now, this you would have seen last time. This is the core of what we were doing. So what we've got, I'll actually go through a little bit since most of you weren't here. That top graph, so the blue section are 100 samples from basically a simulated population that had a mean of 50 and a standard deviation of 10. So basically I took 100 samples of n equals 5, n equals 10, n equals 20, n equals 50. Okay? And the blue had a mean of 50 and the red had a mean of 10. Oh, sorry, the red had a mean of 70. 50, 70. Those are the actual truth, which in research you almost never see. But the truth is that they had different means. They were different. And that their standard deviations were set to 10. If I had samples of 5, could I have told those two groups apart? Sample of 10? Maybe. 95 times out of 100, could I have told that apart?
Yes.
Possibly, yes. 20? I can tell them apart. 50?
Definitely.
Overpowered. Is that what that means? So that's the concept that if you have enough sample, enough power, you can detect differences, very small differences. Yes? Again, that's another way of looking at what I'm the underlying principles of what I'm talking about. And there's the calculations for the standard errors. Fair enough? And so what that interval is that's the 95% confidence interval. And essentially, it is 1.98 times the standard error plus above the mean of the sample and below the mean of the sample. each time. So each line is the sampling mean minus 1.98 times the standard error plus 1.98 times the standard error. That's what that. So these are all confidence intervals, arguably. That's sorry. 1.98 is it's the correlate to the alpha. It's a z-score to the alpha. So 0.05. That's where that comes in. And 0.05 saying I'll tolerate a 5% error. That's just we'll get to that in a moment. So the concept being the larger the sample, the tighter that's going to be. And so I'm going to really believe they're different, which is essentially what that means. Was that helpful, these two, in terms of, yeah, Sarah's my guinea pig. He'll tell me, no, that didn't work in explaining that. Okay, so now we're just going to talk about the critical parameters that you have to make up or find some evidence in the literature to go into your sample size estimation. You're never going to have to calculate this by hand because, and we'll come to that, there are statistical programs around that will just do it. You just have to think of these concepts. First is effect size. So essentially that means if you've got two groups, let's take the simple case that your variable is a continuous variable, let's say it's normally distributed, and so what effect size means, what's the difference between the means of the two groups? So with blood pressure, and say I had some sort of drug that was being used and testing whether it makes a difference, you would want to say if the mean with treatment was lower than the mean without, obviously, and then you're going to ask how big is that difference. The effect size is how big is that difference. Yep. And we tend to think in standard deviations. Fair? So the standardized difference is how many standard deviations difference is there? And so if you say that you want to detect one standard deviation difference versus two versus half, things like that. If I said to you, do you think you'll need larger sample to detect a standardized difference of one standard deviation versus two, which one would require a larger sample, do you think? One standard deviation difference versus two. Yeah, because they're closer together. Fair enough, we'll keep going. And I can come back at any point. These are just numbers, as we talked about. So in the sample size estimation goes alpha and beta. Alpha is the proportion or probability of false positives that you're willing to tolerate. The lower the probability of false positives, the higher your sample size, so that multiplier is higher. So if I want a 1% false positive rate, that's a much larger sample than a 5%. Beta is about power, or the probability of false negatives that you're willing to tolerate. And one question, actually a medical student asked last year, is why are you willing to tolerate, because the standard conventions are 0.5% for alpha and 20% for beta. Why are you willing to tolerate a higher probability of false negatives? And I think that's a good question, actually. Partially because the sample size gets so high, I think. But those are just numbers again. And as you can see, that if you were tolerating and this tends to be one-sided, which is why the numbers are different on beta and alpha. But those are just numbers, and typically 5% is 1.96. I said 98, 1.96, and 20% is that, and those are the two multipliers. And you can think of those as a constant if you go with the conventions. And I'm just giving you where those numbers are from. Now, in terms of calculating, and now we're going to calculate and place some numbers. One way to do it is this beautiful nomogram, where we're talking standardized difference, power, and alpha. So alpha, 1 minus beta, and your standard difference, and you can you can figure out per group. So if your standardized difference is 0.5, you want an 80% power, and a 0.05 alpha, that's about 120. Okay? Whereas if you're willing to tolerate a 1, you can see how much smaller that sample size is. It's 30. So you can use a nomogram like this. Again, the point being the numbers that you will have to come up with are the standardized difference, which is the difference in means divided by the variance, in a sense, the power you want to use, and the significance you want to use. And those are fixed. So it's basically the standardized difference that you need to make up your mind about. There's the formula. Should we just move on? Will that just confuse you? It's there, and you've already done. If I said to you, you actually know what that's in there. I'm just going to move on because I can see the fear in your eyes. Let's move on. But it's there if you want it, okay? Now let's actually talk about how to do them. So they're performed on the primary outcomes because you might have multiple outcomes you're interested in. Let's do the simplest, cleanest thing, which is a randomized controlled trial of two groups of equal size. As we talked about, this is always the standard of a new hypertensive drug. The systolic blood pressure is the continuous outcome you're interested in, normally distributed, we'll say. We'll also talk about it as a binary outcome and illustrating the principle that if you can have your outcome be continuous and normally distributed, increases your power, as in smaller sample size to detect a difference or an effect that you're interested in. Fair enough? So if at all possible, you keep it continuous. But sometimes you can't, and that's because it goes to proportions at that point. Okay, so the other thing of interest. So one is your outcome continuous versus not? And the other is, do you have independent samples versus paired samples? Remember we talked about that concept? So independent samples, men and women. Paired sample means women, time A and time B, or women and their children, or men and their children. Somehow there's a correlation between the results of certain pairs. Fair enough? So continuous outcome independent samples. Your alpha is 0.05. Your beta is 0.2, hence power is 0.8. The difference that you want to detect in the mean of the systolic blood pressures is 15 milligrams per mercury, millimeters of mercury. Okay? And your standard deviation is thought to be about 20. So what's the standardized difference that you want to look at? Oh, I've done it for you. Sorry, I always do this. Let me take that off. It's 0.75. So anytime that standardized difference is less than 1, I hold on to my horses a little bit. Because the general principle is if it's 1, that's going to be, not too high of a sample. The lower you get, the higher the sample's going to go. Jump right in, Sarah. Okay. So, continuous outcome, independent samples. So you can see how wonderful the computer is. This is Stata that we've talked about using, Stata 13. Stata actually is something that St. Vincent's has a license for. I don't know exactly how to get it. You might know. We can find out if you need to. But if you want Stata on your computers, your laptops, those kinds of things, I actually think you should get it if you're doing any kind of study. It's a brilliant program. So, SAMPSI for sample size. First mean, second mean, comma power, standard deviation. You can actually put standard deviation 1, standard deviation 2. You can do all sorts of things, but this is simple, right? The implicit alpha is 0.05. Then it spits out ding, 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 and then it tells you what you need, sample size-wise. So you can see that the computer does a lot of the calculations. It's the dynamic relationship of the principles and the things that you need. And I was talking to Sarah, very similar to thinking about the heart functioning and cardiac output and preload and afterload. It's just relationships, right?
The computer's just reading out that graph that you had before.
Bingo. It's just doing it in the background. And it's much more, it can do a lot more. But nonetheless, same thing, And again, another thing that most statisticians will tell you as you ask them is they don't know anything about anything. A good place to begin is a sample of 20 to 30 per group. It will get you probably. I have people asking me 4 per group is enough. We can have those discussions. And you guys won't have that trouble. Those are people in the lab usually. Usually, possibly 4 is enough, 3 is not. Ideally, we don't want that. We want more. This is with the standardized differences. Or sorry, let's just talk about, this is the other way to do it. Sometimes you don't actually have a mean. It's about relationships, we said, right? So I can say in a putative example that I have group 1 with a mean of 1, a group 2 with a mean of 0.25. I have 80% power and the standard deviation is 1. I'm going to get the same result. So it really doesn't matter that I put the actual means and standard deviations it's the relationships. Fair enough? You look a little unhappy.
That's right.
Yeah? So, you want me to slow down a bit?
It's just that last sentence. So,
Oh, I just said that
Yeah.
you don't need the actual 120 and 105. It's actually looking at the relationship of 120,
sure.
105, and 20.
Yeah.
Yeah, that's why I was saying nothing major. Now, continuous outcome paired samples. Now you can see why it's such a powerful research design. And why research design is important. Again, the alpha is the same, beta is the same. We're looking for a difference of 15 millimeters of mercury pre and post, right? As clinically relevant, the standard deviation is thought to be 20. The standardized difference is the same, and we have paired samples. And this is same thing. I'm just calling this a change. It's pre, and so I have one measure pre, one measure post. Correlation between the pre and post is 0.7. Okay, it's a high correlation. Does that make sense? That means that if I could that they're very much related. The people who are high on systolic blood pressure early will be high later. People who are low will be low later. They'll vary, but they'll lag. You can see that sample has gone down in terms of that. And actually, it's actually 23, right? Because it's the same people you're sampling again. It's not 28 times 2. It's actually 23 people. You're measuring them at 2 different time points. But the hardest thing in the study is collecting participants, recruiting participants. So the sample size is much reduced. So if you can at all do pre and post, have the person serve as their own control. And the reason this works is that the variance decreases considerably because that correlation is there. So binary outcome, independent samples. So again, the same thing we're talking about. And one thing to remember is that the binary outcome, it should be calculated based on the number of events rather than the number of people in the study. And it depends on the proportions. So assuming equal sample sizes, alpha and beta are the same, we're looking for a clinically relevant difference of 10% difference. So 0.2 to 0.3 in the two groups. And you can see how it blows out. Alpha. And actually this is, it blows out partially because I've left alpha of 90. I should have changed that. That's one thing I didn't catch. So it'll be less. It may be like 350 or 300, but it's still much higher. Almost 10 times higher. I've got to remember to do that. I keep forgetting to do that. So, but SAMC can handle it again. So the great thing about this data, for those of you we haven't talked to about it yet, there's all sorts of syntax, and syntax as in any language that you have to follow. But it's easy to figure that out. You type help. You can even do help sample size estimation. It'll give you what to use, and you can click to it. There's some example. Usually what I do is I copy the example and change it. And so it isn't about memorizing any of this. It's more thinking. So this is, in a sense, to show you that this is one way of looking at it, 1, 0, 0.2 to 0.3, right? You flipped what's 1 and 1, 0, and you've got that, which is 0.8, 0.7. It's the same thing. In the sense of whatever you define as 1, whatever you define as 0, one's going to be 80%, one's going to be 20, one's going to be 70%, one's going to be 30. But they're the same thing. I just want to show that. Now, we've talked, so this is probably the key thing, which is play around. Understand the environment of your relationships for your study. And then you can make a pretty educated guess. And you can also then say, what if I don't recruit that many? How many will I have to aim to recruit? Probably 10, 20% more, and then you'll probably get it. Well, how many will I have lost follow-up if I have a pre and post or something like that? So all of these, and you can actually talk around it, and you can, in terms of writing out your protocol and things and asking for money. And you can think about being conservative in that way. And so here's another thing in data again, but this is the power command. So power 2 means, and I'm saying give me a table, keep the power at 80%, keep standard deviation at 1, but I want you to vary the effect size all over the place. Yes? And if I said to you, of course you'll look down here, but don't, do you think it's pretty amazing actually how much of a difference in sample you need when you have a 0.1 to a 1 difference, right? And you can see where it's doing that. You can see the difference in numbers. So there's cost. It's really, and it does beautiful graphs as well. The graphs are a bit harder to interpret sometimes than the tables, I find. So there's that. But you can do that. You can then change this. You can change 2 of them. You can put this kind of thing in here too, and it'll do all of it for you. Can you understand what that means, guys? Oh, sorry. It's just saying, I'm doing it. I'm playing with it now. So the null hypothesis is that the means are equal. The alternate is they're not equal. They're assuming equal variances. Standard deviation of the group in 1 and 2 are the same. Da 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 da. Make sense? Just bit by bit. And we've talked about this. Does that completely make sense? You could actually tell me that now, couldn't you? That's obvious for most of you. So 10%, like I assume you're going to lose. Yeah. So this is, I'll send all this to you. So 1 or 2-sided alpha is always a question, and the answer is always two-sided. Two-sided. Because you're going to have a lot of previous studies on the same research question to even venture into one-sided alpha territory, I'd say. Because what you're saying by doing a study is, I don't know the answer. That means you don't know if it's larger or smaller. Which side is important? So you do a 2-sided alpha. It's also a bit more conservative. Obviously, it's more conservative. So that means the 2-sided alpha means that I shouldn't reduce my false, split it up, decide it's one way or the other. This seems obvious. So why can't we have large sample sizes for everything? It's because we don't have the money, etc. But one question is it ethical to do a study that is underpowered? Is it ethical to do a study that has too small of a sample so that you will never actually understand anything statistically? If you're at risk of doing that, you have to ask what it is you're going to learn from that study. I'm just trying to think. Oh, I actually haven't run over time as is usual. It doesn't always have to be large numbers. I mean, this one's relatively large in terms of 50, but it's still doable. It's doable in, within the reach of even studies that you might be interested in to begin with in your career, as in terms of doing yourself. And as you might expect, that as that research question matures, you're going to go from very small studies to larger ones. Because you're probably, as you go on, interested in subgroups. And anytime you're interested in analyzing subgroups, your power needs to go up. You need to be able to, again, it's 20 or 30 per group that you're interested in. So if you're interested in differences between 2 age groups, then you need to have 20 in both. Wendy's apologizes. She just said that she was Very busy. At this point, this is just the arc that you've gone from 45 to thousands in all of these. One question you have, and I get a little suspicious when the power is too high. And why might that be? Because if you need that much power to detect a difference, then is that really going to be clinically relevant? The difference that you show? That's one question. Because you have enough sample, you can detect a difference in 2 groups or 3 groups. And then that asks the question about how useful that is. I don't think you need these, you answered them perfectly. But one question I'd be interested in is, does this make more sense to you now? Easy.
I think it was helpful knowing that you've got startup, that you can just punch in some numbers.
It's easy, yeah. It is very easy.
But I guess it's always a bit difficult to, like you say, if you don't have, if it hasn't already been done, and if it's a new question, how do you guess your standard deviation, because that's still a number that you're going to have to pluck out, and that's why, we sometimes do pilot studies to sort of get a bit of an idea before we launch in, but... Yeah.
And then the question is, even in doing a pilot, how large does it need to be to feel like you have a stable center,
Exactly.
Does that make sense? Yeah. So in a sense, your first study is often something like that, where you just assess it, because you're working with biomarkers and things, new things, where other people haven't used them.
Not working with anything at the moment, but just, finish the PhD.
Okay. Is it clear to you guys where to find that kind of information? Do you feel comfortable seeking out the information you need to populate some of these things you need for the STATS program? And you don't need a STATS program. If you go out and just Google sample size estimation X, you'll find things online, and they're fine. They're fine. I've just done it in this because this is available to you. One question I have for you, we can keep going, because there's more. In fact, I probably need to go back a bit and talk about the other analysis, which I can do pretty easily. I feel comfortable that you're comfortable with all of this. Most of you weren't at last time's meeting. In terms of the central limit theorem and the like, I think we can probably go on. That's lovely to know. What I'm asking is whether you guys should review that. Should we do another talk where we go through that again for those of you who weren't? It's a new year.
Might be worth going through again, because it's something it seems quite important.
It is quite important, and it's still hard, and nothing wrong with hearing it twice. Should we do this as an out-of-session one, or should we do it next time, or start now? I don't think I should start now because I don't want to break it in half.
I think it might be maybe next time.
Is everyone happy with that?
I think adding on another session might be difficult.
I agree.
Together, so.
I'm just putting that out there as an option. I think that's fine. I think Wendy, I'll do that. That's easy enough for us to do. So what we've been doing for those of you who are just starting is this is sort of a series of lectures. Yeah, what we've really gone through is epi stuff, which on the whole from the presentation is pretty easy to follow. This is the hard bit, to be honest. This bit particularly, I think, is if we can carry forward with it, it'd be really good. Is there anything in terms of the sample size? So one question on the sample size: did you want this to be more detailed? Or is this good at a first cut to understand the relationships?
First.
Yeah. This is what we've been using for the medical students, and they seem to find this helpful. What I think with all of this is it's layered, and this first layer, ideally, you have the concepts down, and those don't start wobble too much later. That you can add on. Do you have any other thoughts? Any additions, pointers for today?